All right, students, let's see if I can help with another one here. Here is Chapter 21, number 31. It says here, from the Maxwell-Boltzmann speed distribution. Okay, so let me write down that equation. It wasn't really derived for you. It's equation 21.42, 21.24 in the Survey book, and it basically says this. I'll say it in graphical form first, that if you have a bunch of molecules in a box, and so here's a bunch of BBs, if you will, and they're bouncing around, as they hit each other, some are going to go fast, some are going to go slow. If you limit to the total amount of energy, you can't have too many that go fast, but a few that go fast. And because they're always hitting each other, you can't have too many that go slow. And then there is some kind of distribution. And so n is being that number at a particular volume, and then n at a particular speed, v, versus v. And the graph looks something like this, where it peaks up. And what this is really saying right here is this then is the biggest number. This is the most probable. This is where if you just randomly reached into this box, sure, some of them would be going slow, but the chances of getting that are really small. And so whatever this n of slow would be. And then likewise, ones over here would be going fast. And so this would be n of things going fast. Okay. So there's very few of them going slow and very few of them going fast. Most of them are in this category. And again, the statistics of this is really beyond the scope of this class. But the class is trying to set you up for future classes and trying to say that with a good statistical background, you should be able to do these random collisions and figure out what is the probability of one's going fast and one's going slow. And that's what Boltzmann did. And the textbook is trying to point out then that you might look at three different ways of describing the speed of our molecules, because really none of them have the same speed. They're all distributed, and whatever speed that molecule has, it's going to change it something like 100 trillion times every second when it collides. So that's kind of this idea. So it seems like somebody's first reaction would be to say, what's the average speed of them? Okay, and then that's fine. However, the average speed is not necessarily the speed that most of them have. And of course, the reason why is this tail end may extend out in a different shape than this drops back. So the graph is not evenly distributed. And that's the way it works. This kind of has a tail to it, and this kind of drops quickly. And so if you look at the average is a little bit to the right of this spot, which we like to say is the most probable speed. That is the speed that most of them have. So the average speed is actually a little bit higher than the speed that most of them have. That's because some of them are way out here going really fast. And of course, another important one to look at is what I like to call the average of the squares square root, because that is the RMS, and that's what it stands for. It says then square it, take the mean, take the average, and then the root of it. And so that's kind of like the average of the squares, and then square rooted. And the reason that's useful is because kinetic energy is related to the square of the speed. And so if you wanted to know the average kinetic energy, you would want to know the average square of the speeds, not the average speed or not the most probable. So all of these are good different ways of describing what is the speed of our molecules. And your author, without much proof, although did do the Equipotential energy theorem, and said that the average of the squares, square rooted, is 3 times Boltzmann's constant times the temperature divided by the mass. And that's probably the easiest one to do, and perhaps even the most important for you to learn for this semester, because you would say, you know, if you took 1/2 mv squared, and then you averaged that, that would be equal to 1/2 Boltzmann's constant times temperature for each degree of freedom. That's the equipotential energy theorem. So if you cancel off the 1/2 and move the m to the other side and then take the square root, you are going to get the square root of the average of the squares. And so that's what we call the RMS speed. So the RMS speed for us is the real important one and the practical one. This particular problem really is just trying to drive home a little bit more that you don't always want to look at the RMS speed or the average speed, or you don't want to always look at the most probable speed. But this problem is about the most probable. Okay, so maybe I blabbed on too much kind of the idea of the problem, but without proof, your author says that this function, this distribution, depends, of course, on n, the total number, and some other factors here, like the mass of the object, and again, Boltzmann's constant, and then the temperature, and then to the 3/2 power. But here's where you get the speed distribution, so it's proportional to the speed squared, and it's also proportional to a decaying exponential, where you have kinetic energy in the numerator, that's at 1/2 mv squared, and you also have the energy part of it, the temperature, that is, okay? And in fact, that's why you can kind of see that at low speeds, this number would be kind of small, and you could just approximate it as 1, so it could be quadratic. And so in this area, this graph would look very quadratic. And then at high speeds, both are going on, but exponentials dominate any power function at large distances. So you get more of a decaying exponential out here. And so this tail end is a different shape than that. And so this one's a little steeper than that. That's what I was saying. It's going to put the average in there. So again, this one is trying to say, okay, what is the most probable speed? So if you were to reach in, what is the most likely one? And that would be the peak of the function. And remembering from your calculus then, the peak of the function is where the derivative is equal to 0, right? The derivative being the slope. So your author even says then, take the derivative of the distribution function with respect to speed, set it equal to 0, and then solve it, okay? Let's see if you come up with the equation that they got in equation 2127. All right, so let me do that. Let me take the derivative of this. And let me think of it in this way. I'll call this the constant a. Let me call this the first function. How about f of v? And let me call this the second function. How about g of v? Because we know taking a derivative, the constant pulls out. And then we just have the product rule. So it would be the first times the derivative of the second plus the second times the derivative of the first. And so I'll take advantage of the product rule. I'll also take advantage that this constant can just be brought over, and so if you divide by a, you still have 0. So there's your 0. So I don't need to worry about all this other stuff. They have no v's in them. All right, so the function would be v squared. Then I've got to take the derivative of this exponential. Now, the derivative of an exponential is the exponential itself. Okay, so I'll do that. And then the derivative of I guess we call the chain rule here, the derivative of the argument here. So there'd be a minus, and there would be the m, the 2, the kbt, okay? And then the derivative would be 2v. Okay, so that's the derivative of g. Okay, so the second one here is then g, so that's e to the minus mv squared over 2 kbt, so there's g, and then the derivative of f, and so f is just the v squared, so that's a 2v. Okay, now, again, maybe the thing to do is to say, well, let's take this and divide by the exponent, if you will. So e to all that junk, e to all that junk, e to all that junk. Which is okay as long as all that junk doesn't equal 0. And remember, a decaying exponent never does equal 0. A decaying exponent looks something like that. All right, so no problem dividing by it. So that would cancel off, and that would cancel off, and we would still have a 0. Okay. Let's see. I guess we could also do something like this. We could divide by 2v. Divide by 2v. Divide by 2v. Okay. Now, again, that's okay as long as v doesn't equal 0. Now, coming back to our graph here, we might ask, well, what about right here? Does the slope equals to 0 there? And it does, but that's not the one we want here. And so does v equal 0, is that a solution? And you can see, yeah, you put in v equal to 0, it does have a solution. So yes, the slope here is 0, but that's a minimum, not a maximum. So again, just maybe being a little anal with my math, I'll say, okay, I can go ahead and cross out the 2 v's, and of course this is still equal to 0 on that side. All right, well, maybe I should rewrite that because I've got quite a bit here. So I still got the v squared here, and it looks like I've got the minus m over 2 kbt still left there. The 2v canceled off and the exponent canceled off. Looks like over here, all of those canceled off, so I'm just left with 1. So if I bring this to the other side, v squared, I'm just left with a 1, and then when I bring this over, it's 2 kbt over m. And so then when I take the square root, the velocity, that gives me a slope of 0. And so this velocity right there, the most probable velocity, is given by the square root of 2 and Boltzmann's constant and the temperature divided by the mass. And then that's what they say, show that the most probable speed is given by that. And so this is equation 2127. Yep, there it is. All right, take care.